Matt Novak from Purdue University, who will talk to us on weak kinetic shock solutions to the Landau equation. Thank you, Matt, very much for coming.
Hi, thank you, Susan, for the introduction, and thank you also for the invitation. I'm very happy to be here. So everything that I'm speaking about today is part of an ongoing joint work with Dallas Albritton at Wisconsin and Jacob Bedrosian at UCLA. All right. Oops, that's an inauspicious start. There we go. Okay, so the goal of my talk is to discuss how we model shock waves. And the familiar starting point for modeling shock waves is a hydrodynamic description. But the main goal of my talk will be to motivate and then describe a description of shock waves at the level of kinetic theory. And the idea here is to construct solutions of kinetic equations such as Landau or Boltzmann, which could rightfully be called shock solutions of these equations. And this is a part of the literature which doesn't have actually very many results. I'll tell you sort of what's known. There's some results for Boltzmann, but none for Landau. And so a very rough statement of the theorem that we prove is that there exist these kinetic shock solutions to the Landau equation, and they have all the nice properties that you would expect of a shock solution. So they're unique, they satisfy good estimates, and perhaps most importantly, they're approximated to leading order in a precise sense by the shock solutions of the hydrodynamic equations. So the goal of my talk then will be to sort of walk you through this story, starting from the hydrodynamic description, moving on to the purpose of the kinetic description, and then telling you a bit about the theorem that we prove. All right, so let's start with the hydrodynamic description of shocks with our favorite toy model for shock formation, the Inviscid-Burgers equation. So we know very well that Burgers develops discontinuous solutions from smooth data. This is the shock formation. So I have a decreasing profile on the left, which as time passes turns into this discontinuous shock solution. And this is a very well-studied process at the level of Burgers, and we know that the entropy condition selects for a unique weak solution for something as simple as Burgers. And one of the important aspects of these shock solutions is the Rankine-Hugoniot conditions. So for my purposes, imagine that we have a traveling wave solution of Inviscid-Burgers. So I posit that my solution has this form, and then I plug that into Burgers. And I want to see if I can figure out what the shock speed is, at what speed the shock moves, as a function of the left and right end states for the shock. And we can see this through the Rankine-Hugoniot conditions. So what you do is you take this equation, you integrate it over the whole real line, and you find that the shock speed times the jump in U, where the jump is the difference between the right and left end states, is equal to the jump in the flux of U. And the flux for Burgers here is, of course, just 1/2 c squared. So this is Rankine-Hugoniot for Inviscid-Burgers. And solving for the shock speed, I get the very familiar formula, which says that the speed is it's the average of the right and left end states, UR and UL. Okay, so let us add dissipation or viscosity into this picture. So we consider viscous Burgers. Okay, so this is a well-posed equation. It won't form a discontinuous shock solution. What it will rather have are traveling wave solutions that have a shock profile, a smooth shock profile. And You can check that the shock speed of this profile is still the same S that we compute via Rankine-Hugoniot as in the Envisage case. And we can further do a bit of dimensional analysis to figure out what the height and the width of the shock profile are in terms of the viscosity parameter nu. Okay, so let's figure this out. So the viscosity parameter nu has units L squared over T. And if I assume that my shock has a small jump, so a jump of size epsilon, then the units of epsilon are the units of U, so that's L over T. And if I want to solve for the shock width, so the width of this sort of transition layer, I need to make a length scale out of nu and epsilon. And when I do so, I see that I get that the shock width is the ratio of nu divided by epsilon. And I can see this then at the level of the smooth profile. So if I take this equation, put it in traveling wave form, and integrate in X, I can solve for U and I get this tangent profile. And it has the epsilon over nu inside the argument. All right, and I should emphasize that if I give you a left and right end state and ask you to solve for a shock profile solution, it will only be unique up to translations of that profile. Any translation will also be a solution with the same left and right end states. So I could restore uniqueness by, for example, fixing a value of U at the origin. Okay, so this is the simplest model of shock formation and shock wave analysis that we have.
Vertical or horizontal translation?
Horizontal. So that the end states are the same no matter where I translate it. Okay, so let's transition now to a slightly more complicated model. So this is 1D compressible Euler. So the unknowns here are velocity, U, density rho, and internal energy density E. And the system of equations is these. So this is conservation of mass, momentum, and energy. And I should point out that the pressure is given by this equation of state, which says that it's a constant multiple of the energy density E, where this multiple depends on some exponent gamma, which is bigger than 1. And the pressure is equal to rho times the temperature theta. Okay, so I want to rewrite these equations in a more abstract but compact form. And I'll do so, of course, by aggregating the unknowns into a vector. So I'll put density, momentum, and energy into this vector. So density is just rho, momentum is rho U, and then this is the energy. With this unknown, then the 1D compressible Euler equations can be written in this abstract form for the unknown vector valued function U. And the flux F of U is something that I could write down the formula from examining the nonlinearities in the compressible Euler equations. All right, and it's a classical fact that 1D compressible Euler develops shocks from smooth data, somewhat analogous to what we had for Burgers. And just like Burgers, I can solve for the shock speed of a traveling wave solution using the Rankine-Hugoniot conditions, which say that the speed times the jump in U is equal to the jump in the flux of U. All right, so let us add viscosity into this picture by considering now the 1D compressible Navier-Stokes equations. So the left-hand side has stayed the same. And then on the right-hand side, I still have 0 in the density equation, but then I have these dissipation terms in the momentum and energy balances. And it's again helpful to abstract in some sense this system. So the left-hand side is still the conservation law that I had from Euler. And then the right-hand side is some dissipation term where I write B of U as abstract coefficients they're the coefficients inside the viscosity. So they depend in some possibly nonlinear way on you. All right.
So viscosity depends on temperature in this case.
Yes, it's a function of temperature, theta, in this setting. It's bounded below so that I have all the nice properties that I want, but it is a function of theta. Okay, and just like as we saw in viscous burgers, that when I add viscosity, the strict jump solution is replaced by a smooth traveling wave profile. The same thing happens for compressible Navier-Stokes. So this is the equations in traveling wave form. And I solve by integrating in x. And what I find is something which looks like an ODE. It is an ODE, but it's a slightly degenerate ODE because this viscosity coefficient, B of U, there's no viscosity in the equation for the density. So this is a degenerate ODE in some sense. But nonetheless, you can construct smooth traveling wave solutions to 1D compressible Navier-Stokes. And this was done by Weil and Gilbarg, and then somewhat more recently, Maida and Pago. Okay. So this is the hydrodynamic description of shocks. But what I want to convince you now is that there's good motivation to study perhaps a kinetic description of shock waves. So I'm quoting here from a survey paper from '76 of Fisden et al. And Fisden quotes G.I. Taylor, who points out that some clue to the nature of the process of shock formation and propagation can be gleaned by taking the perspective of the kinetic theory of gases. And Fisden further comments on this kinetic versus hydrodynamic description by saying that in the regime where the Mach number is rather large, say larger than 2, the hydrodynamic description leaves something to be desired. It's not as accurate as one may hope. And so I've pulled a few pictures from this survey paper. So I suppose they're not rendered that largely, so it's hard to tell what they say. But the picture on the left is at a rather smaller Mach number. And at the smaller Mach number, there's some deviations from the experimentally observed density profile, but they're milder than the deviations that are observed for a density profile, a larger Mach number. Okay, so the takeaway from this Fisden survey is that, especially in the transition layer, the hydrodynamic description deviates somewhat from what is observed in shock profiles. And this deviation is exacerbated at higher Mach numbers. All right, and so somewhat more recently, there's a survey of Kevin Zumbrunn on Boltzmann shocks. And he points out that, like I mentioned on the last slide, the shock transition layer is rather inaccurately described by Navier-Stokes theory, but could better be described by a kinetic model such as Boltzmann. And Zumbrunn further points out that the development of methods at the level of kinetic theory for treating large amplitude kinetic shocks is really one of the most important open problems in this field. So that could be considered as a very nice dream theorem, namely studying large amplitude kinetic shocks and proving things about their existence. Okay, but we're very far from that goal at the moment. Okay, so this is then the motivation for studying a kinetic rather than a hydrodynamic perspective on shock waves. All right, So if we're going to adopt a kinetic theory perspective, I should say a few things, basic facts about kinetic theory. Okay, so the unknown in this kinetic equation is the particle distribution function F, which tells me the probability of finding a particle at a point Tx traveling with velocity V. And so on the left-hand side of this equation, I have free transport. And then on the right-hand side, I have a collision operator, which attempts to model what happens when particles collide. So this is a bilinear collision operator, so two particles colliding. And the prefactor in front of this collision operator is the Knudsen number, which is the ratio of the mean free path, so the path that particles trace before colliding, compared to the macroscopic length scale. So the physically relevant regime is that in which the Knudsen number is very small, which means that then the effect of collisions is greatly amplified. Okay, and there's a whole menagerie of various collision operators. I'll just write down two classical ones. So this is the Boltzmann collision operator with so-called hard sphere potential and angular cutoff. And I won't use any specifics about this formula in the rest of my talk, so you don't have to memorize it. But this is the formula for the Boltzmann collision operator. It's bilinear in the particle distribution function F. And the collision operator that I'm particularly interested in today is the Landau collision operator. So this is again a rather complicated formula, which I'll revisit a little bit later and tell you about its properties, coercivity, and whatnot. But I just wanted to put it on a slide once before saying a few things about how to study these kinetic equations. Okay, so what are some basic properties that are satisfied by these collision operators? So if we start with the Boltzmann collision operator, the first important property is the conservation of mass, momentum, and energy. And I can compute the mass, momentum, and energy associated with the unknown F by first integrating over all velocities. So this gives me a particle density, which is a function of space and time. If I integrate instead the particle distribution function against the velocity, over all velocities, I get the momentum rho u. And then finally, if I integrate against v squared, mod v squared, I get the total energy. And the important property of the collision operator is that its range is orthogonal to 1v and v squared. So that when I take the entire equation and I integrate it against 1v and v squared, the right-hand side disappears and I get conservation of mass, momentum, and energy. All right, and one can show that all the equilibria, namely the functions for which the collision operator vanishes, are Maxwellians. So these are just Gaussians parameterized by three quantities. So they're parameterized exactly by the hydrodynamic quantities of density, velocity, and temperature. So this is the form of a Maxwellian with density rho, temperature theta, and velocity u. And of course, if I compute the mass, momentum, and energy associated with this Maxwellian, I should have recover the mass, momentum, and energy given by rho, u, and theta, which is exactly what I have here. So the Maxwellian has the expected hydrodynamic quantities. All right, and the final property of this collision operator is that it satisfies the H theorem. So this says that the entropy is decreasing in time. All right, now the Landau collision operator satisfies basically the same properties at an abstract level as the Boltzmann collision operator. So we have conservation of mass, momentum, and energy. We have that the only equilibria are Maxwellians, and we have the H theorem. Okay, so let me say now a few words about the hydrodynamic limit. So the hydrodynamic limit is going to be the fundamental tool which connects for me the compressible fluid picture and the kinetic picture. So this is a little diagram that I lifted from Francois Goltz's book. The hydrodynamic limit is this arrow here connecting kinetic theory and hydrodynamics. And what we expect is that in the limit of Knudsen number to 0, which is the hydrodynamic limit, the effect of collisions becomes very strong, and F should converge at each point in space and time to an equilibrium of this collision operator. And we know that these are the Maxwellians. So morally speaking, we expect that F converges to a Maxwellian parametrized by the hydrodynamic quantities of density, temperature, and velocity. All right, so there's a few different ways to approach a hydrodynamic limit. One of the classical ways is a Hilbert expansion. So I simply posit an asymptotic expansion for the unknown F in terms of the small parameter, the Knudsen number. And then I plug this expansion into the equation and balance the various terms in the Knudsen number. All right, and what happens when you analyze this balance is that the leading order term, so F0, it ought to be equilibrium of the collision operator because I need the terms with epsilon minus 1 to vanish on the right-hand side. And so that tells me that F0 is exactly a Maxwellian, which is parameterized by hydrodynamic quantities of rho, u, and theta. And the question then becomes, can I find an equation which is satisfied by the density, temperature, and density, velocity, and temperature associated to the leading order portion of my expansion? All right, and we can find pretty easily the equation satisfied by rho naught, u naught, and theta by taking the equation and integrating it against the collision invariance of 1v and v squared. So here I've just integrated against 1, so I just integrated in v. And you find out that rho naught and u naught satisfy exactly the conservation law for the mass from compressible Euler. All right, now the issue with the Hilbert expansion is that it gives compressible Euler to leading order, but it doesn't give me compressible Navier-Stokes to next leading order. And if I'm studying smooth shock profile solutions of Navier-Stokes, I need an asymptotic expansion which can extract Navier-Stokes from the kinetic equation. And the right asymptotic expansion for this purpose is the Chapman-Enskog expansion. And as I'll explain on the next slide, the hydrodynamic limit emerges precisely in the setting of weak shocks. So the jump of the shock from left end state to right end state is only of size epsilon. All right, so what I want to do now is explain this Chapman-Enskog expansion in the context of weak shock profiles. Okay. So what's the setting of our problem? It's the traveling wave Landau equations with one-dimensional spatial dependence. So t and x are both taking values in r. I'm still assuming a three-dimensional velocity. And in this setting, the Landau equation becomes v1 minus the shock speed times dxf equals qff. Okay, and let me fix the Knudsen number equal to 1, so I don't see any prefactor in front of the collision operator. And let me assume that F is describing a shock that has width epsilon inverse and height epsilon. Now, my goal is to explain to you how this shock height epsilon leads to the hydrodynamic limit. And I can find the hydrodynamic limit by non-dimensionalizing the length scale. So I replace x with epsilon x. So now the shock width is 1. The height is still epsilon. And upon this non-dimensionalization, this is the equation that I find. So this is an equation which has 1 over epsilon in front of the collision operator for a small value of epsilon. And this is exactly the regime of the hydrodynamic limit. All right, so the takeaway here is that small shocks correspond precisely to the setting of the hydrodynamic limit. All right, so we will study small shock solutions for the Landau equation. All right, so how does this Chapman-Enskog expansion work? So the first step in the Chapman-Enskog expansion is to decompose your unknown into a macroscopic quantity, which is a Maxwellian. So I use the letter mu for Maxwellian. And this Maxwellian should have the same hydrodynamic quantities as the full solution F. So if I integrate F against 1v and v squared, and I get the density, momentum, and energy, that should be equivalent to integrating this Maxwellian against 1v and v squared. And that means that this lower order term, lowercase f, is purely microscopic. So it doesn't see the hydrodynamic quantities of mass, momentum, and energy. All right, so this is my decomposition. And my goal is then to find an equation which is satisfied by the macroscopic quantities of mass, momentum, and energy. And when I take this equation, the Landau equation, and I integrate against 1v and v squared, I find macroscopic equations which on the left-hand side look exactly like compressible Euler with one-dimensional spatial dependence in traveling wave form. So the left-hand side is compressible Euler. And then the right-hand side depends on the microscopic portion of my solution, lowercase f. So this is a closure problem, one second, in which I want to model the microscopic portion, lowercase f, in terms of the macroscopic portion to leading order. And in doing so, I'll obtain a closed system of equations for the macroscopic portion of the solution. Yes, you had your.
I was gonna ask how you decompose. Is it through this?
So I just
solving this system?
So I take f and I integrate against 1v and v squared. That gives me 5 numbers, a density, a velocity, and an energy. And then I form the Maxwellian that corresponds to that density, momentum, and energy. And that's mu f is this Maxwellian. Okay, so I need to find a leading order asymptotic for the microscopic portion of my solution, lowercase f. And in order to do so, I take my full equation and I linearize it around the Maxwellian corresponding to my macroscopic quantities. And when I do so, I find this equation. So this is the equation that is obtained by taking the linearized collision operator around the Maxwellian mu f and projecting the Landau equation off of the kernel of this linearized operator. So this P mu f perp is the projection off of the kernel of the linearized Landau operator around mu f. And now I extract a leading order asymptotic for lowercase f by inverting this L, which I'm allowed to do because I projected off of the kernel. So the leading order asymptotic for lowercase f, I throw away the nonlinear term. And I also throw away this term with lowercase f here. because lowercase f is already small. And when I hit it with the dx, I pick up another factor of smallness because my shock width is epsilon inverse. So that dx picks up a power of epsilon. And so now I've come up with an asymptotic for lowercase f purely in terms of the macroscopic quantities in mu f. All right, so this is the Chapman-Enskog expansion then. And if I take this expression for lowercase f and I plug it back into the right-hand side, what I find is precisely compressible Navier-Stokes. Yes, so we take this expression, plug it into the macroscopic equations, and we get that this mu f solves compressible Navier-Stokes to leading order. All right, and this then gives me a good guess for a solution of the Landau equation. Namely, it's, I call it FNS for F Navier-Stokes. And it's precisely the guess that I have from this Chapman-Enskog expansion. So it's the Maxwellian, which I call mu NS. This Maxwellian solves Navier-Stokes. And then I have this lower order microscopic portion that came from the second part of my Chapman-Enskog. All right, so with the Chapman-Enskog expansion in hand, I can tell you what our theorem says. The theorem says that if you consider the traveling wave Landau equations, then there exist solutions which may be decomposed in the following way. So the leading order, these solutions are precisely the lifting of the Navier-Stokes solutions to the kinetic setting that we obtained in the Chapman-Enskog expansion. And then there's a lower order perturbation, which satisfies a bunch of nice estimates, which I don't need to parse at this time, but I can take derivatives in x and v, and I also have some weights in x and v in this estimate. All right, and this kinetic shock solution is unique up to spatial translations, just like I would expect, and the class of solutions which satisfy this decomposition and these estimates. All right, so this is our theorem. It says that we can construct kinetic shock solutions which are approximated to leading order by a Navier-Stokes shock profile. Okay, so what is the state of the art for kinetic shock solutions? Well, all the existing work is for the Boltzmann collision operator. So there's no results prior to our result for Landau. And the first construction for Boltzmann was due to Nikolenko and Thurber. Shortly thereafter, there was a generalization due to Kaflish and Nikolenko. And these proofs use a sort of generalized Lyapunov-Schmidt procedure, which from our perspective was quite difficult to understand. And so what we really took inspiration from was a later construction of Metivier and Zumbrunn. And what Metivier and Zumbrunn did was they reproved the theorem of Kaflish and Nikolenko, so a construction of weak shock profiles for Boltzmann, but they didn't use this Lyapunov-Schmidt procedure. Rather, they used the Chapman-Enskog expansion that I just described, and then they took that solution, they plugged it into Landau, and closed a fixed point argument for the remainder. And this is really the inspiration for our approach to constructing kinetic shocks for Landau. All right, and I have a few other results listed here. So there's a result of Liu and Yu, which proves that the Boltzmann shock profile is positive. And then there's invariant manifold results of Liu and Yu and Poggen and Zumbrunn. And I want to point out that the driving force behind this study, namely the large shock problem, is still completely open. And it doesn't even seem like the physicists have a good prediction for what the asymptotics of a large shock profile should look like. So hopefully we'll get there someday. But at the very least, we ought to be able to solve the weak shock problem first. Okay, So in my remaining 10 or 15 minutes, I'll tell you a bit about our proof. So of course, the goal is to construct weak shock profile solutions to Landau. And as I already described, the first step is this asymptotic expansion, which extracts to leading order the Navier-Stokes profile FNS as a good approximation of the full solution F to the Landau equation. All right, and once I have that good guess FNS, Navier-Stokes solution, I should just study the linearized equation, which is associated to the residual. So this is the difference between a putative full solution and my lifted Navier-Stokes solution. So that linearized equation is what I have written here. And what it looks like is linearized Landau with the linearization around the Navier-Stokes solution equals some right-hand side. Okay, so my plan should be to collect all the estimates and knowledge that I can for this linearized equation. And once I have that knowledge in hand, I can solve for the residual via a fixed point argument. So that's the outline of the proof. Take the Navier-Stokes shock profile, plug it into Landau, it's a good guess, and then solve a fixed point for the residual. Okay, so we've boiled down the analysis then. The fixed point argument is essentially classical and there's not really anything interesting there. All the interesting work is in this linearized Landau equation. Okay. So my goal is then to study this linearized equation, and I will do so by decomposing the solution of this equation into microscopic and macroscopic components. So the macroscopic component lives in the 5 dimensions of density, velocity, and temperature. And I find the macroscopic component by integrating my unknown against 1v and v squared, and then decreeing that the resulting density, momentum, and energy are equal to the density, momentum, and energy associated with Fmac. And Fmic then has no density, no hydrodynamic quantities associated to it. All right, and my analysis then will consist first of microscopic estimates, which focus on estimating Fmic. And as I'll explain, the linearized Landau operator is essentially coercive for the microscopic portion of my solution. And in order to close my estimates, I need then macroscopic estimates for Fmac. And Fmac, as I'll explain, lives in the kernel of the linearized operator. So those are the 2 ingredients that I need in order to analyze this linearized equation. Okay.
What's the difference between Fmac and Maxwellian associated with F? Seems like the compositions are similar. That's what
Say again?
What's like this seems like F equals mu of F, which is the Maxwellian of F plus little f. And then so how does the Maxwellian
Yes. Good question. So you should think of the solution F as living in some giant function space associated to particle distribution functions. And inside that function space, there's a manifold of equilibria. So this is a manifold of Maxwellian equilibria. So if I have a solution F, say it lives over here, I can project it onto the manifold of equilibria. this gives me mu f. And since I'm studying a linearized equation, I actually want my macroscopic component f mac to live in the tangent space to the manifold of equilibria at the point mu f. So f mac is in the tangent space at uf. So f mac lives in this affine subspace. That's a good question. Okay. So let's start with the microscopic estimates. So the first step is to perform essentially some algebraic manipulations which ensure that L2 is the natural function space for the unknown. And in order to ensure this, you replace the unknown f with some Maxwellian corresponding to the left end state mu L raised to the 1/2 times a new unknown lowercase f. And plugging this into the Landau equations, I get an equation for lowercase f, in which I've isolated the linearization around the fixed left end state, and I've put the difference between the left end state and the true solution of Navier-Stokes into an error term on the right-hand side. And the reason I've done that is because I expect mu ns minus the left end state to be order epsilon because I'm assuming small shocks. So that means essentially that this term is going to be perturbative in my analysis. All right, so the linearized operator around this fixed left end state has a 5-dimensional kernel, which is precisely the tangent space to the manifold of equilibria at this point. And so this is the parameterization of that 5-dimensional kernel. It corresponds to the macroscopic quantities of density, momentum, and energy. And if I project off of this 5-dimensional kernel, then I have a coercivity estimate for the linearized operator. So this coercivity estimate, it's a little ugly, but what it basically says is that up to some weights, which depend on the velocity, I have control of the gradient of f after projecting off of the kernel, and also control of f and L2, again projected off of the kernel. So this is a coercivity estimate for the portion of my solution which doesn't live inside this macroscopic subspace. All right, so with this coercivity estimate in hand, what I should do is take the equation and multiply by f and integrate by parts. Okay, and that's basically exactly what we do. And what you find is that the projection of f off of the kernel is controlled by LF hit with f, the linearized operator. And from my equation, I know that that's controlled by the right-hand side. And the right-hand side picks up the difference of mu ns minus mu L, which is small because I'm in the regime of small shocks. And then I have to estimate f. And so I decompose that into this piece, which can be absorbed onto the left-hand side due to the weak shock. And then the macroscopic component, which I'll have to control in a minute. And of course, whatever my right-hand side is in some unspecified function space. Okay, so I will have to come back later and close this estimate by telling you something about the portion of f which lives in the kernel of the linearized operator. Okay, and this estimate I can bootstrap X and V derivatives and X and V weights in order to control the projection off the kernel of F. All right, now the last ingredient in my proof then is an estimate for the macroscopic component of my solution. Okay, so the macroscopic component, it's exactly this Fmac from my decomposition. Fmac lives in the kernel of the linearized collision operator, and it has the same hydrodynamic quantities as the full solution F. And now I need to estimate Fmac. All right, so what you find is that if I perform a linearized version of the nonlinear Chapman-Enskog expansion that I used earlier, remember the full Chapman-Enskog expansion parameterized the solution in terms of Maxwellians living on this manifold. So the linearized Chapman-Enskog should parameterize the solution in terms of elements of the tangent space to this manifold. And the linear equation, which is then satisfied by Fmac, is exactly linearized compressible Navier-Stokes. So you should think of the nonlinear Navier-Stokes equations for Maxwellia living on this manifold projected onto this linear subspace as giving me linearized compressible Navier-Stokes. And so linearized compressible Navier-Stokes is something that we can analyze basically from classical knowledge of compressible Navier-Stokes. So if you take the construction of the Navier-Stokes shock profile, you extract a bit of spectral knowledge out of it, then you can derive an estimate for the solution of the linearized Navier-Stokes equation around that shock profile. And what the estimate basically says is that because my shock width is order epsilon inverse, when I attempt to integrate and estimate the solution of linearized Navier-Stokes, my estimate says that the Fmac is controlled by epsilon inverse times whatever the right-hand side in my linearized equation is. All right, and then I take this estimate for Fmac and I plug it back into my estimate for the microscopic portion of F, which required knowledge of the macroscopic quantities. And I basically use the fact that I have weak shocks in order to close this loop. The weak shocks give me a prefactor of epsilon, which then closes these estimates. And that is all. And let me thank you for your attention.
Questions and comments? So all of this works for small epsilon. Supposing you had more energy in the system, your shocks were bigger.
Right.
So does anything carry over, or it's...
Well, you won't be able to use the hydrodynamic limit because the large shock won't give us the small Munson number. So one could imagine perhaps some sort of global bifurcation argument which could help us find these large shocks, but there's really no clues about how to run such an argument.
Can you go back to the, you have two pictures showing some experiments and then the prediction.
That's right. Oh, wow.
So these are experiments for 3D, right?
Well, it's a one-dimensional spatial dependence. So this is the graph of the density profile as a function of the one-dimensional spatial.
Oh, okay, so the
variable.
experiments are even there for 1D as well.
Yeah, I think these experiments are in the setting of
Anything that
one-dimensional
can be
spatial
said about
dependence.
higher dimensions, any predictions or anything?
Uh,
Like even how would you define, comparing right? Two endpoints in the two-dimensional case. Like, how would you generalize that?
Good question. So in the higher dimensional case, I think there's some geometry of shock structure which is going to come into play. But that's not my area of expertise, and that's not what we're treating here. We're just treating the simplest case. But I think at least in the simplest settings, it should be possible to extend some of this to the higher dimensional case.
Other questions, comments?
So is there any like numerical knowledge about these large shocks that you said that are not in the regime of the hydrodynamic limits?
Not that I'm aware of. I mean, well, these numerics are very old, and it's hard to find anything newer. There doesn't seem to be much.
It's curious. There's so much numerics out there, one form and another. I would have thought this was a type of problem that would attract people.
What would you say about numerics for Boltzmann or Landau, Julie?
I don't know, yeah, I think the large shocks are hard, right? You can, strong shocks are hard. But I have a quick question. So the result is about the traveling type solutions.
Uh-huh.
So what can you say beyond, let's say, if you don't have this answer?
So all the weak shock profiles are all traveling waves.
Yeah,
So if I had some other wave pattern, like a rarefaction or something,
Yeah.
there are results for kinetic versions of those wave patterns. I know some of these are due to Dwan. But those arguments are a little different. Because in that setting, the Chapman-Enskog expansion is a little more powerful than it is in our setting.
Thank you.
Other questions or comments? And let's thank Matt again.